This video is going to take a look at the process to conduct a hypothesis test for two means. And the context we're going to be looking at is comparing two colleges. So College A provides a sample of 11 graduates who took, on average, 4 math classes each with a standard deviation of 1.5 math classes. We're going to contrast that with College B, who provide a sample of 9 graduates who took, on average, 3.5 math classes. With a standard deviation of 1 math class. Does this prove at the alpha equals 0.01 level that graduates of College A took more math classes What we have here is two samples that are being compared to each other. It's not a paired data because we don't have before and after. The numbers don't come in paired. It's not a claim about a mean that we're comparing to, but we've got two actual samples. We've got the sample of College A, and we've got the sample of College B. We also can see in here several key values. College A, sample size 1, I'll call it sample of College A, had 11 graduates. The average X bar from College A was 4, and the standard deviation from College A is 1.5. Now, College B has a sample size for B of 9, an average for B of 3.5, and a standard deviation for B of 1.0. Those are going to be the values we use as we run through our hypothesis test. Now, hypothesis tests always follow the same 6 steps. The first step is we have to define the hypothesis that we're going to test. Our null hypothesis is that the average from College A is exactly the same or equal to the average from College B. The alternate hypothesis, what we're trying to prove is that College A took more. So the average from College A is greater than the average of College B. If we were to draw a picture of this situation, what we've really got is an average difference of 0 between the two schools, and we want to show that A is bigger. We want to show that we have a right tail test. So for C, we're going to calculate the test statistic. To find the test statistic, the first thing we need to know is how to find the standard error. And the standard error we found out is the square root of the first standard deviation squared divided by the first sample size plus the second standard deviation squared divided by the second sample size. We also said it's going to be useful to know what those standard deviations squared are, so let's find those first, actually. So for the standard deviation of group A squared, that's going to be 1.5 squared, or 2.25. That's going to be helpful to us. Also, the standard deviation of b squared is going to be equal to 1.0 squared, which is just 1.0. So when we put those values into our square root, the first standard deviation squared is 2.25. Over the first sample size, there were 11 graduates. Plus the second standard deviation squared is 1.0, divided by, there were 9 graduates in that group. And if I do this on my calculator, I get 0.56 for my standard error. And now I can move to finding my test statistic t. For my test statistic, we're going to take the average from the first group, subtract the average from the second group, and divide by the standard error. So for this one, it's going to be the average of the first group was 4 math classes minus 3.5 math classes divided by the standard error of 0.56. We end up with 0.89 is our test statistic. Now, to find the p-value, I'm going to try and squeeze this on one screen. We'll see if it fits. To find the p-value, we first have to know how many degrees of freedom that we're actually working with. Now, the degrees of freedom was that big ugly formula. It's going to be the standard deviation squared of the first group. We found out that after squaring, that's 2.25, divided by the sample size of the first group, which is 11. Plus the standard deviation squared of the second group, which is 1.0, divided by the sample size of the second group, which is 9 squared, divided by, and then in the denominator, it's 1 over 1 less than the sample size, which is 10, times the standard deviation squared of 2.25, divided by the sample size of 11 squared, plus 1 over 1 less than the standard deviation, times the standard deviation squared divided by the sample size squared. When I do all of that, I'm getting 17.40 degrees of freedom. We need to know that because to calculate the p-value, we're going to use equals. It's a right-tailed test. So on Excel, we can say t.dist.rt for the right tail. The test statistic we found was 0.89. The degrees of freedom, which we just found, was 17.40. I can put that into Excel, and we get our p-value of 0.1929. And that can go right on our picture. That's the shaded area of 0.1929. So if that is our p-value, the decision we're going to make, if the p-value is 0.1929, alpha we said was 0.01, our p-value we see is bigger, then the alpha, when we have a bigger p-value, we are going to fail to reject our null hypothesis. And I'm running out of space, so I'm going to move down below to put our final interpretation. The final interpretation always focuses on the alternative hypothesis, putting in context that we failed to get the alternative. We failed to prove that the average of A is bigger than the average of B. We can say that there is not sufficient evidence, because we failed, at the alpha equals 0.01 level. To conclude the graduates of College A take more math classes than graduates of College B. And that is how we conduct a hypothesis test to compare two samples to see if they have a different mean.